we need to cover this examine the developing this interaction diagram. Let me turn off my camera so does not comes in the way. All right, now let's read this one. Determining the key points A, B, C, D, E. So what does it A, B, C, D, E means? So today we're going to work on section number 10. I think section 8 beam was done, section 9 slab was done. Now the last topic is section 10. All this theory we're going to talk later. Okay, there you go. So the standard does not put the A, B, C, D. They have given the different name, which I'm going to talk about. A, B, C, D. That's what they want you to find. Can you tell us this point, this point, this point, and this side? Basically, you need to find a load and moment. Load and moment. Load and moment. Load and moment. So you need the two values for each point. You need the load and moment here, load and moment here, load and moment here, load and moment here, because you have x-axis and y-axis. You need to locate this one in the two-dimensional space. You need this value and you need this value. So that standards will going to help us. That's the good part of these subjects. Section capacity line, column section, so on. In the case there is a 1200 millimeter of reinforcement in each face. So there is a tensile reinforcement and compression reinforcement. Bending takes place about the x-axis. So the bending will take place about x-axis. FC dash, please make a correction here. FC dash 40 megapascals and yield strength of the steel is 500 megapascals. Typically, you know, the beam that we use generally we have 32 megapascals and so on, because we have this bending, tensile and all. But this column generally has a more compression load, so we generally use more higher strength like 40-50 megapascals and so on. Now let's start with these examples. Let's start from top down, meaning that let's start with easy points. You can start with any point. These points are independent, by the way. There is no relationship between those points. You can start here, you can start here, you can start here, you can start here. But I like to start with easy points. Let's start with this easy point. What is the easy point? Meaning that you don't need to calculate the moment here. Moment is 0 here. You just need to calculate the load, because that 0 comma load. So x-axis is 0, y-axis is the moment. And they have the name of this one is A in our examples, but here they say the squash load point. Squash load point meaning that your column is under pure axials. Pure axials meaning that if I have a columns here, I'll just have a bottom here and I apply the load here, just like this. It's no bending, nothing else. Just apply this. You have a plate or something. You can put the let's say you have this strong plate, you can weld on top of it, and you just apply the load on the plates like this. Okay, so that is the squash load that they want to calculate. So easy. Now we have a squash load equations that was given in our lecture notes. It does not tell us this equation here, but they ask you to identify yourself without bending, and that is denoted by NUO. So basically we have this load moment curve, and this first point is 0 moment. This is, by the way, 0 moment, and NUO, that's the name of that squash load, NUO. So if I squash load, and that is NUO. Right, so to find the squash load, by the way, is quite simple. It's just addition of our concrete force and also addition of our steel force. So basically force in concrete, and this is a compression force, by the way. This is compression force, because column generally have under the axial load no bending, no tension, and then you have a compression force in steel. Compression force in steel. So that is easy. We need to add them together. So if I want to calculate the force, by the way, the force is equal to stress times area. That's a simple equation that we know from our first year, that force is equal to stress times area. So what is the stress in concrete? Stress in concrete is alpha 1 FC dash, that is the stress in concrete, times by the area of the concrete, plus stress in the steel, because it's a yield strength. We say that this steel will be under yielding times by the area of the steel. All right. So this is the stress in concrete. Stress in concrete, and this is your stress in steel. Stress in steel, and this is the area of the steel, and that is your area of concrete. Okay, so let's find each parameters one by one. So I need alpha 1. Alpha 1, by the way, is representing your reducing your capacity. FCDS is given 40, but the alpha 1 is given here in this close 10.6.2.2. 1 take away 0.003 FCDS. So alphas is 1 take away 0.003 FCDS, and that is to do with the close 10.6.22. Now what is alpha 1? Alpha 1 is basically, they talk about that when you have a cylinders, you generally make the cylinders 100 millimeter by 300 millimeters, and you test it under the compression load, and you find out this FCDS 40 megapascals. But when you put the same concrete in the columns generally are short or long, but they are not 300 millimeter by 100 millimeters. You might have this kind of a column. When you put the 40 megapascal concrete which is coming from cylinder test, the strength reduced. So this alpha 1 basically take into account the size effect. So size effect meaning that your capacity is reduced, and FCDS was 40 megapascals here. So let's plug the value. So let me use my calculators. 1 take away 0.003 times 40, you get 0.88. See, 12% of your concrete compressive strength just gone because you have a size effect. So stress in concrete is alpha 1 FCDS. Basically you have 0.88 times by 40. So look at that. Standard does not want you to use 40. That is coming from your cylinder test, but it just wants you to use 35.2 megapascal. 12% penalty come from the size effect. Area of the concrete. Now area of the concrete can be found. Let's say gross area you can find 400 by 600. So gross area take away area of the steel, that we can get it from the so 400 by 600 is the gross area millimeter square, and the steel area is 1200 and 1200. So there are total 2400 millimeter square. 2400 millimeter square. So let me type it up. Take away 2400. So you have a concrete area of 237,600 millimeter square. Right. Let me try again. Take away 2400. Yep, that is correct. So we found area of the concrete and yield strength, and area of the steels we already know. So the squash load equal to concrete stress, which is 35.2. Concrete area is, let me write megapascals on Newton per millimeter square, times by 237,600 millimeter square. That is the force in concrete. And yield strength of the steel 500 megapascals given in our examples. This one steel 500 megapascal is generally n bar, so we default use 500 megapascals. And then your area of the steel is 2400 millimeter square. So the squash load is 35.2 times 237,600 plus 500 times by 2400. So you have 9563520 newtons. So if I want to make it kilonewton, 956.5 kilonewtons. So it's just 9564 kilonewtons. So the first point that we're going to get is easy, that your moment is 0, load is 9564 kilonewtons. So this is moment, this is load. So let's put the points here. First one, that 0,9564 kilonewtons, and that is our first point, point number A. Or if you like to say this is a squash load point, close 10.6.2, that is the informations here. We're going to use these informations later. And by the way, you need to make this check. Sorry, I think I missed that checks. So I think we need to make a revision that your alpha 1 should be between 0.72 to 0.85. Yep. So let's make a that revision. That check here. Check should be 0.72 alpha 1 to 0.85. So this is not good. So we need to use 0.85. 0.85. So let's say 40 times 0.85, you got 34. And here let's change it to 34. So 34 times by 237 600 plus 500 times by, just make these corrections, you have 9278 400 Newton. So 9278.4 kilonewton. So you generally get 9278. So 9278 kilonewton, and this is 9278 kilonewton, right? So I hope you understand that check that we just make it. Now the second points, that is point number A, we found quite easy because the moment we no need to calculate. Now the second ones that we're going to do it is name of the second point is a decompression point. And please note the line from this point to this point is linear line. Linear line meaning that you have to draw the straight line. From here to here you need to draw the curve line. Okay, you can see this is a parabola kind of thing. So you need your arcs here. Arcs meaning that you just need to have some good balanced hand where you can have a straight line and then like a curve. So that's kind of a smooth things that you need to do. So this is squash point we found, and the name of the second point is called decompression point. In our example we call it B, but this is a decompression point. Now decompression point is given in clause 10.6.2.3. that's 3 lines, very helpful. Decompression point is calculated taking the strain in the extreme compression fiber is equal to this one, and strain in the extreme tensile fiber is 0 using the rectangular stress block. Okay, that is quite useful. Quite useful meaning that you have these cross sections for us, and in that cross sections if I draw the strain profile, that it says that this steel here is 0. That's what it says, right? That in this point the strain in here is 0. Right? That's what it says. So the strain in the extreme tensile fibers equal to 0. So strain in the extreme tensile fiber is equal to 0. That's what it says, and the strain here is 0.03. That's what it says, right? You can see here. So then you have a extreme compression fibers is equal to 0.03. So this is because look, this is bending about this axis. Because how do I know that is a bending? You can because this is symmetric. Let's say bending is going in this way, right? Because is a uniaxial bending. So you have a load here with some eccentricity. So this is become your tension, this is become your compression. If you have a eccentricity on this side, then same thing, but it's a symmetric, so your answer would not change, right? So in that case they say that okay, compression strain take 0.03 and tensile stress take a 0. So this is a strain, and you know the stress as well from our theory, that this strain is 0, then stress is 0 here, right? Thus this is stress profile, let's say. And then concrete is not fully done. So this is a stress block. You remember from our beam example, gamma KUD. Do you remember that they talking about the stress block, that you need to use this rectangular stress block 10.6.2.5. So the detail is given here, that alpha to gamma value is given here, same like in the beam one. We can use that stress block to calculate the stresses in this one. And the force is, by the way, the center one here. So that is the force in the concrete, and let's say force in the steel, because we have this force in the steel as well. And there is no force here, this force is 0 here, there is a 0 force here, because 0 strain, 0 stress, 0 force. So we need to find some distance as well. Let's work out one by one how we going to find those stresses. Okay, let's calculate the load first, because we need to find these points, right? We need to find these points. So in that case, we need to find this load here, and we need to find these moments here. I think we know this load is 0.9278 kilonewton, but we know that this load would be less than 9278 kilonewton. Keep an eye on the answers, okay? Don't just blindly follow that one, because these points, otherwise if you have this one, then your axial load strain curve would be follow this one. No, that is not good. So you need to have a 9278 less than that one, and moment would be greater than 0. So let's calculate the force. The force that we're going to calculate, let's calculate this force. Is there a name for that one? They did not put any name. Let's put some name, NU, because this is NUO. So this is NUO, and O is the pure, and we also call this squash load. That's the name as well. Squash load. We also call this one. We also call this pure axial load, pure axial compression load. That is another name. Standard is saying that squash load as well. So that's NU. So let's remove O because it's not pure one. So NU. So NU would be force in the steel plus force in the concrete, because both are going in the same directions, because all the forces, you can assume that all the forces are going here. So NU is, let's say NU is like a equilibrium. So if you have NU going in this way, this internal force is equal to external force. You can say that all the force is going in this direction, and the NU is a force that you need to calculate. So let's calculate this force in the compression and force in the concrete. So this is the force in concrete, compression force. By the way, there is no tensile force here, and there is a force in steel, but that is a compression steel, okay, not tensile steel. There is a one more CT, tensile force, but that is 0, because that's, if I put that CT, but that is 0 right now here. Now concrete compression force, let's say force CC, just we put the concrete compression force CC is equal to stress times area, right? The same area, same philosophy that we used before. Now let's calculate the stress. Stress is alpha 2 abscess. Then stress in the concrete compression is alpha 2 abscess. What is alpha 2? Let's check. Alpha 2 would be 0.85, take away 0.015 abscess, and alpha 2 is greater than 0.67. That's the check we need to make it. And that is 0.85, take away 0.0015 abscess, and abscess should be, alpha 2 should be greater than or equal to 0.67. That is coming from close 10.6.2.5. Now in that case, 0.85, 0.015, concrete compressive strength given in our example 40 megapascals here. So that 40 megapascals. So if I use my calculator, 0.85 take away 0.0015 times by 40, you get 0.79. You get 0.79, which is alpha 2. So stress By the way, this should be greater than 0.67, so therefore it is okay. So stress in the concrete, same like before, right? We do you remember that in the squash load we calculate the stress alpha 1, we have alpha 1 for squash load, but here we have a bending, like we have eccentric loading. By the way, this one is now we are applying the eccentric loading. Okay, for this second point that we are talking about, that we have a eccentric loading. Okay, so it's no more like axial load, it's a eccentric loading. So stress in the concrete is alpha 2 is 0.79 times by 40. So we have 0.79 times by 40, you get 31.6 megapascals. So that is the stress in the concrete. Area of the concrete we know. Stress in the steel, concrete steels. So let's say stress in steel or compression steel, by the way. Compression steel equal to, let's put that CS, compression steel. CS is equal to stress times area. Now, someone might say, how about we take 500 megapascals? No, the 500 megapascals that we're going to take if the steel is yielded. This 500 megapascals is the steel is yielded. But look at this. Steel, we don't know whether steel going to yield or not. So let's take if the steel is yielded or not, because I think neutral axis is far away, so it should be yielded. But let's calculate that the strain in the in this strain here. Let's say this is ESC. Let's say steel strain. Let's calculate ESC. Now to calculate ESC, let's say we have some dimensions given, I believe, that you have a 674 on each side. Okay, let's do it. So we have a this whole length is 600, from here to here is a 74, from middle of this one to here is a 74. Now if I want to calculate this whole distance, then 600 take away 74. So 600 take away 74, you get 526. So you can see similar triangle. This is the one triangle that I can take, and there is another triangle that you can take is this triangle, right? Because they have same angles, so we can take a ratio. So let's talk about this first, that 0.03 divided by this whole length is 526. 526. By the way, this triangle, that 0.003 and 526 triangle. There is another triangle, the red one. I think this distance would be 526 take away 74. 526 take away 74, you get 452 this distance. So there is a second triangle which is ESC and 452. So let's say ESC on 452. Is it right? Yes. So in that case, let's 0.003 times 452 divided by 526. So you get 0.0026 as a ESC. What is the yield strength? Yield strength of the steel would be FSY on ES. 500 megapascals given, and for steel we have 200 megapascals yield strength. So 500 over 200, that is 0.0025, and that is given in our standards too, that your, I think the maximum strain in the reinforcement is 0.00025, that is the yield strength given, and the mathematics also given here. So you can see ESC is 0.0026 is greater than ESY, which is 0.0025. In that case, your steel is yielded. So in that case, if the steel is shielded, we can take the stress is equal to 500 megapascals. Now we have all the details to calculate these CS and CC. So let's say calculate this. Nu is equal to force in the steel and force in the concrete, compression force in the concrete. Now this is the stress times area of the steel plus alpha 2 Ft dash, that is the stress times area of the concrete, that is 500 megapascals yield strength. Area of the steel is for this compression one, let's say 1200 millimeter square. We don't take 24 because the tension one is 0, so you have this 1200 millimeter square plus alpha 2 Fc dash. We calculated that, right? Alpha 2 Fc dash, here you go, alpha 2 Fc dash 31.6. so we have 31.6 megapascals, and area of the concrete we calculated before. Area of the concrete 237,600. So let's plug that. 237,600 millimeter square. So in that case, you have 500 times 1200 plus 31.6 times by 237,600. You get 8108,160 Newton, meaning 8108 kilonewtons. Right? So that sounds good. Let's check that it's below that value. Yes, it's below that one. So he's here. We need to find that one, 8108. Right? So that is perfect. Now to calculate the moments, we just need to use that diagrams to calculate the moment. The moments that we're going to calculate, I think we have some room there or no? I think here you want to calculate. Now there is one term that I like to introduce is called plastic centroid. Plastic centroid. Now what is plastic centroid? The plastic centroid, the cross sections that you get, the point where when you apply the load at that point, you don't have a bending. Now because this is symmetric, if you take the left side of this one, it's a symmetric. If you take this side, it is symmetric. Symmetric cross sections meaning your steel is symmetric. You can see that this is a symmetric cross sections about the x-axis and symmetric cross sections about the y-axis. So when you have a symmetric cross sections, your plastic centroid would be acting in the middle. Middle means where the geometric centroid is. So it's just like in the middles, meaning 300 here. Let's say 300 here and here, because 600 and up, and this is 200 by the way, and this is 300. So because you have a 400 here. So I hope you understand plastic centroid. Plastic centroid is the point where you apply the load and it give you the no bendings, right? So for examples, if you have a unsymmetric cross sections, for examples, if you have a 2 bar here and then 4 bar here, then your plastic centroid would be unsymmetric. It's not a symmetric cross section. So in that case, you need to calculate the plastic centroid. The plastic centroid, let's say dP, that you need to calculate. How are you going to calculate dP? dP is equal to sum of the force times the distance over the sum of the force, meaning that you can calculate the force in here, force in here, force in the concrete, and each distance from the respective. So that's how you calculate the distance, the plastic centroid dP. But in our examples, we don't need to calculate the plastic centroid dP because it's just given in our not given, but it's a symmetric. So we just know that when this force act, they will be in this one. So this plastic centroid would be at 300 millimeters because that is just in the middle. Now this distance is 74, you know that, right? So this is a 74. This distance is, you can calculate that is gamma d divided by 2, right? That distance is gamma d divided by 2. You can calculate that, gamma d divided by 2, and the gamma value that we're going to get is this one, 0.97 take away 0.025 Fc dash. So gamma value, we can just calculate that. I think you know this gamma value from your previous 0.025 FC dash. So 0.97 take away 0.025 times by 40. So in that case, take away 0.025 times by 40, you get 0.87, which is greater than equal to 0.67. So therefore it is okay. Now, so you have 0.87. Distance D is just the day 526, I believe. We have this distance D 526. 526 divided by 2. So you have 0.87 times 526 divided by 2. You get 228.81 millimeters. So let's take it 229 millimeters. So this distance is from here to here 229 millimeters. So now let's take the moment at the about the plastic centroid, because when you take the moment about plastic centroid, it will not going to create any moment. So this CS times by this distance and CC times by this distance. I hope you understand that. So let's give the name MU, moment, MU and NU. So moment. So let's say what was the force in the this one. This is the force in the steel. So let's say force in the steel is 500 times 1200. It's give you 600 newtons. That is the force in the steel, that is CS, times by this distance. This distance CS from here to here. How much this distance? So 300 take away this 74, right? I hope you understand that, right? Because you have this plastic centroid is 300, this distance is 74 given. So 300 take away 74, it's giving me 226. So this distance is 226. So distance is 226 millimeters. Plus, because they are going in the same directions, so that is CS, CC, and I think we calculate the CC. We have CC here. So let me calculate 31.6 times 237, 600. You get 7508. 160 Newton. That is your CC. Is by the way just multiplying 31.5 times 237, 600. And the distance from CC, because this distance we know 229. And if I want to find this distance, so I know this is 300. 300 take away 229. 300 take away 229. You get 71. So you get 71 millimeters. So let's find out this moment. 600,000 times by 226 plus 7508, 160 times by 71. So you get 668, 679, 360 Newton millimeters. Divide by 1000, divide by thousands to get kilonewton meters. So 669 kilonewton meters. Right. So now we have everything that we can plot it the next point. So we have this point, straight line, and this point is 669 kilonewton meters, comma 8108 kilonewtons. 8108 kilonewtons. This one 0, comma, how much was that? 9278. So that is 9278. So I hope, do you have any questions so far? And 9278 kilonewtons. All right. So if you don't have any calculators, any problems, we can go for the next one, which is the I think I need to go through this balance point and the pure bending one by walk you through, because I think we might not have any we may not have times to writing it up, but I hope you understand the story so far. Now we finish all the story here. I think we finished this one. Okay, now here we are talking about this balance point. Balance point meaning, so we done this one, was quite easy. Alpha 1 FC dash times area of the concrete plus FSY times AS. Just the stress in the steel, stress in the concrete, we take both steels and we find this one, zero moment. We found this one, all the forces, this is the clause that we're going to use. Forces in the steel, forces in the concrete, sum them to get the force. Moment, force times the distance to the plastic centroid of the steel, and force of the concrete times the plastic centroid. That's how we get the moment. And this is a straight line, by the way. And one more thing, when you check your columns, let's say you know your design axial load and design moment. If your design axial load and design moments falls under this surface, your column is safe. If it falls here, you need to redesign, and probably generally redesigning means you need to just include more reinforcement and so on, and you need to put your columns down. Look, this is not a magical curve. In the real world, you can't just say that, okay, if tiny bit is sitting here, it means that tiny bit sitting here, it means that it's failed. No. This is just an indicator for us to what is the like a boundary for our columns to be failed. So it is very, I can't say this, and standards will not going to say this, okay, this is safe and unsafe. Okay, this is just the way that they want to design this. This is a surface that is useful for designing your columns. Okay, so that's, but I think in the real world they will say, okay, sorry, in the book or in the theoretical, say this is unsafe, this is safe, and this is unsafe. So this is a balance point. This is the balance point where you remember that it's balance point. Also we have it in the beam. The balance point meaning that your strain values that you're going to get in the tensile strain value. So meaning that your let me check. Okay, so what is the balance point? What is the balance point? Balance point meaning that your steel here is at the yield, exactly at the yield, 0.025. It's very difficult to get one, but it's in the theoretical, it says that your loading is applied, loading somewhere. Let's say you load here or load here or load here, somewhere that your load in a way that, by the way, it's eccentric load. Okay, so it's not load here. This is the pure axial load. If you apply the load in a way that on that load your steel will be at the yield like a 0.0025 exactly, and your concrete at 0.003. That is the balance. That is the balance, meaning that, okay, this is the point. So this balance meaning that this below this point is your ductile failure. Like you can see this is the ductile failure. If you draw the line, then you have ductile failure. Above this line is a brittle failure. Like brittle failures meaning that your steel is this steel is not yielded. So you remember that your neutral axis is somewhere here. So your steel is not yielded. Do you remember in the beam that we want to have a tensile? Look, we want to have a this tensile reinforcement should be at yield, right? So if you look at this before, they are neutral axis is here, they are not yielded, right? There is a strain here in the zero. What is the strain here in zero? That is not good, right? Because we don't have only compression. So our neutral axis is here. Now our neutral axis is going in the middle where our strain is yielded, and then if you go, the neutral axis is going above, like far away from the tensile steel. That's how we get this one. So it's basically your, there is no neutral, that's neutral axis is passing from the middle, so there is no any issue. But here your neutral axis is passing from the bottom rear. That's how you get the strain zero. This one, your neutral axis is going above, far away from the tensile rear. This one we have folder. Okay, so that's how it's just framing it up. So your neutral axis we need to find this neutral axis in a way that this is at the yield. This is a balance point, by the way. The standard does not say anything. Yeah, they do not say. They want you to figure it out by yourself. They did not give you any information because they know from your beam you know how to calculate this balance one. So for balance one, your tensile strain is 0.0025, which is yield strain, and your compressions is zero. In real world you might not have these kind of points, but for theory we have this one. So if I know this one and if I know this value, I can calculate the depth of the neutral axis, right? Where the depth of the neutral axis should be when your tensile still at the yield and compressions, the top reinforcement of the compression reinforcement, extreme compression reinforcement 0.03. So let's take a triangle, that this triangle here, this triangle, which is 0.03 over dn. Okay, so that is good. So this triangle is done. Now let's take the second triangle. Second triangle would be this one. These triangles. Second triangle, this one. And angle here and angle here is same. So in that case, we can take the ratio that this second triangle would be EST, horizontal distance like here, divided by this distance from here to here, this distance, right, from this point. So I know this is 526 because it's given in our example. 600 take away 74 is 526. 526 take away dn, that will give me this 526 take away dn here. Now simplifications, just I want to calculate EST, just bring it here, dn here, 0.03 over 0.0, and you can just find out dn because only one unknown value is, oh, by the way, in EST you can just put straight away here 0.025, 0.0025. So in that case you have only dn unknown. Okay, so you can calculate this dn is equal to 287 millimeters. So that dn is the dn that will telling me that you're still at yielded and your concrete has 0.003. So stress in the concrete, I think alpha 2 FC that is the stress, and I think we calculate alpha 2 0.79. Do you remember that alpha 2 we calculated before? In here we have calculated alpha 2. Alpha 1, yes, oh here you go, alpha 2 we calculated this one, and the gamma value does not change because it depend on FC dash only. So 0.79, 40, gamma value we calculated 0.87, dn we know 287 and 400 is the B, right? You know this theory, right? You have this like this, you have this stress profile, right? Like this, you have these stresses. So the area would be this gamma KUD times by B. So that's what the area of the concrete. Where is it? Here. That's here, and then you find this stress in the force in the concrete. Now we don't know whether this top reinforcement would be at yield or not because your dn would be close to this strain value in the top rio. Let's check it whether it's yielded or not. So similar triangle, ESC dn on 40. So this distance from here to here, and ESC over this distance from here to here, 0.03. Same like similar triangle story. And you know this ESCs become 0.0022, which is less than 0.025 yield strength. So top reinforcement is not at yield. So if it's not yielded, not an issue, because then we can't just use 500 megapascals. We just need to reduce it based on this strain. So if I know the strain, the stress would be just multiplied by Young modulus. So I have this stress 446 megapascals instead of 500. So the force in the top steel is stress times area. You have 535 kilonewtons. As I mentioned, at the tensile reinforcement is at yield. So you have 500 megapascal. We already know this one, that bottom reinforcement has this one. So now again, you remember these diagrams. Only the difference from the previous diagram and this diagram that we have these forces. Previous diagram meaning that these diagrams here. We take these diagrams. In here, we have just only addition of, instead of 0 we have this CT, right, the tensile force. All other details are exactly the same. Probably those values are changed, but the theories are same, like the moment. So I think the same concept, that you have this force, you have this force, you have this force. So you have all the compression force going this way, so positive, tensile force negative, so you have 3091 kilonewtons. Similarly, we take the moment about plastic centroid. We take the moment about plastic centroid, meaning this force times by this distance. So that is this distance. This force 535 times by this distance, and this force, and by the way, all are going same direction. This is anti-clockwise. This is also anti-clockwise. This is also anti-clockwise. So all the anti-clockwise. So all the moments are positive. That's I taken here. And this force. So basically, this force times by this distance, this force by this distance, this force by this distance. Okay, we just taking the moment about this plastic centroid. And plastic centroid, we take the moments, so we know this moment value 809 kilonewton meter, which is by the way should be more than what we predict. Yep, 8669. So you have about 809 kilonewton meters, and the load is 3091. So that is fine. 3091, which is below this one. So that is good. Looks nice so far. So I hope you don't have any issue to calculate those 3 points: squash load point, decompression point, your tensile reinforcement, tensile stress is 0, tensile stress is 0, like a tensile stress is 0, tensile force is 0. In here you have a steel, bottom steel at the yield, and compression has a 0.03, so you can find a decompression point. Now this is pure bending. Pure bending meaning that this is exactly the same like a beam. There is no any axial load, 0. It's called pure bending point, MU0. The pure bending point meaning your column is become the beam, meaning that you don't have any axial force. It has only the moments. So in that case, only the moments, you have pure bending point. So you can just design it as a beam, right? Doubly reinforced beam. So here you started. Look at that. You know this doubly reinforced one, where you don't know this strain, you don't know this strain. You only know that this is the concrete compression strain is 0.03, but you don't know what is the strain in the top reo, what is the strain in the bottom reo. So if you have two unknown, then you can't figure it out what is the depth of the neutral axis. In that case, we need to have a trial. You remember that examples in our beam examples that we have a trial value. You can try 100 millimeters, and then you calculate the strain here, you calculate the strain here, then you calculate the stress, then you calculate the force on the each component. Once you calculate the force on each component, then you check the equilibrium. If it is not 0, you try again some number, dn equal to 40. By the way, dn equal to 40 meaning that we are just putting this one from here, so your strain here is 0. So that is this. So say this again, you calculate force, check the equilibrium, is 214, is reducing, that's okay. Move on, let's try 60. Again, you calculate the strain in the top reo, stress in the top reo, and then tensile force in the bottom reo, compression force in the concrete, and check the equilibrium. Yes, it's negative, so it should pass these values, and you just do the interpolations, and you can find the dn value of 65 millimeters. I hope you understand this this trial one. Do you remember this trial one, right? We used doubly reinforced beam, and we found that dn value is about 65 millimeters. That will give me the equilibrium, because you can see here somewhere about equilibrium. So that's 65 millimeters works. Once you know the 65 millimeters, then you can just do the same procedures that you have these. By the way, this become your tensile steel again, because your neutral axis is just passing that one. So that is compression all tensions and follow the same procedures. Same procedures meaning that you have these force times distance about the centroidal axis, and you can find this. By the way, this force is 0, so you don't need to calculate the force because the force here is 0. Because the force is 0, that's how we find the force is equal to 0 here. For that case, we need to just calculate the moment, right? By the way, there was 600 times by this distance, and so on. So you can calculate this this moment. So pure tensions, I think if you want to calculate the pure tensions, here is quite simple. You just need to have a top and bottom rho, and you can just find the, because you know this, you have these two steels, and concrete is not good in tensions, they are 0, so there is no force for the concrete, only steel. So you just have a 1200 kilonewtons as a tension. This is not required, this is just an additional information that you needed. Someone might say, why is not symmetric? Because you have a concrete here, concrete is helping here. Here you have 0 concrete, you don't have any concrete, only steels. So therefore you have these only 1200 kilonewtons. So this is the whole diagrams. First one is moment is 0, you have this value, then you have these values, and then you have balance point, and then you have pure one, and then you have a 0 moment, and you have this tensile force. So I hope you understand that. Sorry, the last the pure one is just I quickly run through, but if you go through these notes, I'm sure you will follow it up, because it's just same as B. It's just this point. This point is the design of doubly reinforced beam. Right? If you know all the details, if you can design the reinforced concrete, you will, and the axial force is 0 here, so only just the moment that we need to calculate. We have about 6 minutes, but let me know if I have missed anything, or do you need any more details. I hope by these lectures, or if you go through by yourself, I hope you, if someone give you the columns, someone give you like as a header mentions, if you are like become a forensic engineers and there is a recent earthquake in Melbourne and you are trying to investigate trying to investigate whether the columns are under a failure condition or not. If someone give you columns and all the reinforcement details, you are in the position to get this, get this, get this, and get this. If you want to have a tension one, I think it's quite simple here. If you like to get it, it's just additional information for you. So I hope you understand that. This balance point is just the one that will give you that this is the brittle failure and this is ductile failure. Brittle failure meaning that your bottom rho, which is the tensile rho, is not at yielded. So from this point below, your tensile reinforcement is at yielded. But unmute yourself or